last part of this activity is to explore and make explicit the issue of what happens when we have more than one asymmetric or chiral center. So here are some examples of stereoisomers with two chiral centers. One of the things that's mentioned here is compounds with more than one asymmetric center can have a max of 2 to the n stereoisomers, where n is equal to the number of chiral centers. So again, another calculation that we need to do in this course, although a very simple kind of calculation. So for this molecule of 2-chloro-3-bromopentane, there are 2 chiral centers. So the max number of stereoisomers, and I didn't say enantiomers, and I didn't say diastereomers, just stereoisomers, would be 2 to the 2, 4. And so we need to consider the possibility of having 4 stereoisomers. So I've set up these Fisher projections, and to make this a little simpler, I've already designated the configuration for this chiral center and this chiral center. Now in terms of naming the carbons in this molecule, this would be 1, 2, 3, 4, 5. So at carbon number 2, in this particular Fisher projection, it's an S, and you can take a minute or two at some point and confirm that it's an S. At carbon number 3, it's an R. Now actually this makes it quite simple then to fill out the absolute configuration for the rest of these Fisher projections. Because remember that if one enantiomer at carbon number 2 has an S, the other enantiomer has to have an R. So I should be writing here 2R, because of course this is 1, 2, 3, 4, 5, and it will be 3S. So this reinforces the idea that an enantiomer will have completely opposite configurations on the chiral centers. Now moving to molecules 3 and 4, yes, we can go through the trouble of assigning absolute configurations, but we can also make some comparisons. So I'm looking on carbon number 2, and I can see that the orientation on carbon number 2 is the same in molecule 3 as in molecule 2. So I can say, oh, that's 2R. And then I can see that carbon number 3, the orientation is the same as in molecule 1. So this would be 3R. And therefore, over here, this is going to be 2S and 3S. Now, of course, if our first structure is wrong, it makes everything else wrong. But if our first structure is right, then everything else falls out nicely. Now, as it turns out, there are indeed 4 stereoisomers here. Each one of these molecules is different. As you can imagine, and what you're asked to do in key question number 6, we can designate the relationships of these different things. So for instance, molecules 1 and 2 are, of course, enantiomers. And in a similar fashion, 3 and 4 would be enantiomers. And as alluded to earlier, you can only have a pair of enantiomers. But of course, we can have a whole bunch of diastereomers. So without getting ridiculous, we can designate, for instance, 1 and 3 as being diastereomers. And when I say ridiculous, is we could go on representing a lot of different combinations. So these guys are diastereomers. And then, for instance, 1 and 4 would be diastereomer as well. Remember that diastereomers are stereoisomers that are not enantiomers. But we can also equally say that 2 and 3 are diastereomers and 2 and 4 are diastereomers. So here's an example of having 4 stereoisomers. Let's turn our attention to the next example. And in a similar fashion, you can see that I've set up these Fisher projections, and I've designated what the absolute configuration is for the 2 chiral centers in molecule 1. Now, just to set the stage, let's say this is 1, 2, 3, and 4. And therefore at carbon number 2 we say it's an R, and at carbon number 3 we say that it's an R. We have also drawn the enantiomer, and in drawing the enantiomer, of course, then it would be 2s and 3s. And again, this would be 1, 2, 3, 4. You can see that we've also drawn one of the other stereoisomers, which would be a diastereomer of the first two. And in making a comparison, I can once again label this 1, 2, 3, 4. At carbon number 2, I'd say, well, that's a 2R. And at carbon number 3, that would be a 3s. Now, I can draw a mirror image. And so I've got my carboxylic acid here and my carboxylic acid down here, and my OH groups and my OH group, and of course the hydrogen. And you might ask yourself, well, what's the relationship of these two structures? But of course, perhaps you realize that although we have chiral centers, there is a plane of symmetry. And because there's a plane of symmetry, molecule that I've designated as 3 is not chiral. It does not have an enantiomer. Its mirror image is completely superposable. Now this introduces a new term. We would refer to molecule 3 as being a meso compound. So a meso compound has 2 or more asymmetric centers, so we see 2 chiral centers, and has a plane of symmetry. Therefore, it is not chiral, nor would it be optically active. So again, we had a formula for the maximum number of stereoisomers, which is equivalent to 2 to the n, and we have 2 chiral centers, so that's 2 to the 2, in other words 4. But understand, this is the maximum potential number. So potentially there could be 4 stereoisomers. However, if one of our stereoisomers is a meso compound, this means we'll not have the full complement of stereoisomers because it doesn't have an enantiomer. It's interesting to look at some of the properties of these various stereoisomers. So if we compare, for instance, the molecule 1 to molecule number 2, you can see that they have the same melting point. They have the same magnitude of specific rotation but opposite direction. And they have the same solubility in water. So of course all the physical properties are the same except for optical rotation. The diastereomer is going to have different properties. So that's our meso compound right here. So its melting point is 146. Of course, it has 0 specific rotation because it's not chiral. And of course, it has a different solubility in water because it is a different compound. Note the last line. We have our racemic mixture of the 2 enantiomers, 1 and 2. And note, because we have a racemic mixture, therefore a set of impurities, if you will, the melting point is actually different than the melting point of the individual enantiomers. Of course, we have 0 specific rotation because the pair of molecules as a racemic mixture is not optically active. It's kind of interesting that although independently, in the pure form, each enantiomer has identical melting points, when you combine them as a mixture, it's considered to be an impure mixture, and therefore the melting point is elevated. This ends our presentation of chem activity number 11 in the corresponding videos. Of course, we will do more practice in our live sessions.